Tonight, we're going to explore something so fundamental that once you understand it, you'll never look at the universe the same way again. Look around you. Everything is spinning. The Earth beneath your feet completes one rotation every 24 hours. The Moon orbits us. We orbit the Sun. The Sun orbits the galactic center. Electrons spin around atomic nuclei. Galaxies spiral through the void. Black holes drag spacetime itself into rotation. But here's the question almost nobody asks. Why? Why does everything spin? Where did all this rotation come from? The answer involves one of the deepest truths in physics, a truth that Richard Feynman helped illuminate through his revolutionary understanding of symmetry and conservation. And by the end of this journey, you're going to understand exactly why the universe simply cannot help but spin. Before we dive in, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you probably take for granted. The fact that you're spinning right now. Not metaphorically, literally. As you read these words, you're being carried along by Earth's rotation at roughly 1,000 miles per hour if you're near the equator. That's faster than most commercial jets fly. You don't feel it because there's no acceleration. No sudden change in that rotational velocity. Everything around you is moving at the same speed. The air, the buildings, the ground beneath your feet. But you are spinning nonetheless. And it's not just Earth. The Moon orbits our planet once every 27.3 days, locked in a gravitational embrace that has persisted for over 4 billion years. Earth and the Moon together orbit the Sun once every 365.25 days, which is why we add a leap day every 4 years. The Sun itself is moving, orbiting the center of the Milky Way at about 230 kilometers per second. That's over 500,000 miles per hour. At that tremendous speed, it still takes the Sun roughly 225 million years to complete one galactic orbit. Astronomers sometimes call this period a cosmic year or a galactic year. The last time the Sun was at this position in its galactic journey, dinosaurs were just beginning to appear on Earth. The time before that, complex multicellular life was only starting to colonize the land. The Milky Way itself is rotating. The entire galaxy, somewhere between 100 billion and 400 billion stars, is spinning like a cosmic pinwheel. The exact number is hard to pin down because counting stars from inside a galaxy is like trying to count trees while standing in the middle of a dense forest. You can see some clearly, but most are hidden behind others, obscured by dust and distance. But all of them, every single one, participates in this vast galactic rotation. And galaxies themselves move within clusters, which move within superclusters, all participating in a cosmic dance of rotation and revolution that spans billions of light years. The Milky Way is falling toward Andromeda at about 110 kilometers per second. Our local group of galaxies is moving toward the Virgo cluster. Everything is in motion, and much of that motion is rotational. Zoom in instead of out, and you find the same story. Every atom in your body contains electrons existing in orbitals around the nucleus. Those electrons possess something called spin, an intrinsic form of angular momentum that we'll explore in depth later. Protons and neutrons in the nucleus also spin. Even light, which has no mass at all, carries angular momentum when it's circularly polarized. From the quantum to the cosmic, everything rotates. Everything spins. Everything possesses angular momentum. But why? This is the question that fascinated Richard Feynman, one of the greatest physicists of the 20th century. Feynman was born in 1918 in New York City and went on to make fundamental contributions to quantum electrodynamics, particle physics, and our understanding of the quantum world. He won the Nobel Prize in Physics in 1965. But beyond his technical achievements, Feynman had a unique gift. He could take the deepest, most abstract principles of physics and explain them in ways that illuminated their fundamental nature. He wasn't interested in memorizing formulas or accepting rules without understanding. He wanted to know why the universe worked the way it did at the most fundamental level. In his famous Feynman lectures on physics, delivered at Caltech in the early 1960s, he devoted considerable attention to symmetry and conservation laws. He saw these not as mathematical conveniences, but as windows into the deeper structure of reality. And when it comes to rotation, the why turns out to be one of the most beautiful stories in all of physics. It involves symmetry, conservation laws, and the very structure of spacetime itself. By the end of this exploration, you'll understand not just that everything spins, but why it must spin, why the universe has no choice in the matter. Let me explain what I mean by rotation in physics, because it's more subtle than you might think. When we say something rotates, we mean it has angular momentum. Angular momentum is, in simple terms, a measure of how much rotation an object has. A spinning top has angular momentum. A planet orbiting a star has angular momentum. A figure skater doing a pirouette has angular momentum. A hurricane swirling over the ocean has angular momentum. A galaxy wheeling through space over hundreds of millions of years has angular momentum. But angular momentum isn't just about spinning on an axis like a top. It's about any kind of rotational motion around any point. When Earth orbits the Sun, even though Earth isn't spinning on its axis with respect to the Sun in that orbital motion, the orbital motion itself represents angular momentum. Earth is moving in a roughly circular path, and that circular motion around a central point constitutes angular momentum. Physicists call this orbital angular momentum to distinguish it from the spin angular momentum of a rotating object. Angular momentum depends on three things: mass, velocity, and the distance from whatever point you're measuring the rotation around. More mass means more angular momentum, all else being equal. Higher velocity means more angular momentum. Greater distance from the rotation axis means more angular momentum. The mathematical formula combines these factors in a specific way, but the intuition is straightforward. A heavier object moving faster in a wider circle has more angular momentum. This last point, about distance from the rotation axis, is crucial and explains something you've almost certainly seen. When a figure skater pulls their arms in during a spin, they speed up dramatically. When they extend their arms, they slow down. Why does this happen? Because angular momentum is conserved. When the skater pulls their arms in, they're reducing the distance of some of their mass from the rotation axis. Since angular momentum must stay constant, the speed of rotation must increase to compensate. The skater isn't creating energy or angular momentum. They're just redistributing what they already have. This conservation of angular momentum is the key to understanding why everything in the universe spins. But we need to go deeper. We need to ask why angular momentum is conserved in the first place. What fundamental principle of nature guarantees that rotation, once it exists, cannot simply vanish into nothing? This is where Feynman's approach becomes so illuminating. He built his teaching around the insight that the deepest truths in physics are connected to the deepest symmetries. And he was absolutely right. In physics, a symmetry means that something stays the same when you make a particular change. If you move an experiment from one place to another and it behaves exactly the same way, that's a symmetry. The laws of physics are the same here as they are a mile away, or 1,000 miles away, or on the other side of the galaxy. That's called translational symmetry. Space doesn't have special locations where the rules are different. If you rotate an experiment and it behaves the same way, that's rotational symmetry. The laws of physics don't care which direction you face. If you do an experiment facing north, you get the same results as facing east or south or any other direction. You can orient your laboratory however you like, and the physics works identically. This seems obvious, almost trivial. Of course, the laws of physics don't depend on which way you're facing. But this apparently simple observation has profound consequences. There's a remarkable theorem in physics called Noether's theorem, named after the mathematician Emmy Noether, who proved it in 1918. Her theorem reveals something extraordinary. Every symmetry of nature corresponds to a conservation law. The fact that the laws of physics don't change over time, that symmetry gives us conservation of energy. The fact that physics works the same everywhere in space, that gives us conservation of momentum. And the fact that physics works the same regardless of direction, that rotational symmetry gives us conservation of angular momentum. We'll explore Noether's theorem more deeply in the next part of our journey. But the key insight is this: conservation laws aren't arbitrary rules imposed from outside. They're necessary consequences of the universe's symmetries. The fact that space has no preferred direction means angular momentum cannot be created or destroyed. It can only be transferred from one object to another. So when you see something spinning, you're not just seeing motion. You're seeing a manifestation of the universe's fundamental symmetry. The spin exists and persists because the universe doesn't favor any direction. The spinning top keeps spinning not because of some active force maintaining it, but because the universe has no mechanism to make the spin disappear. But this raises another question. If angular momentum is conserved, if it can never be created, where did all the angular momentum in the universe come from in the first place? How did rotation get started? The answer is both simple and profound. It came from the initial conditions of the universe and from the impossibility of perfect symmetry in a real physical system. Let me explain what I mean. Imagine you have a perfectly spherical cloud of gas floating in space. If this cloud is perfectly symmetric, with no rotation at all, and if the forces acting on it are also perfectly symmetric, then it would collapse straight inward under gravity and never develop any rotation. Every particle would fall directly toward the center. No spin would emerge. But perfect symmetry doesn't exist in the real universe. There are always tiny fluctuations, tiny asymmetries. Quantum mechanics guarantees this through the Heisenberg uncertainty principle. At the smallest scales, nothing is perfectly still or perfectly symmetric. When a cloud of gas begins to collapse under gravity, these tiny asymmetries mean some parts are moving slightly differently than others. Even if the net angular momentum is close to zero, it's never exactly zero. There's always some residual rotation, however small. And here's where conservation of angular momentum becomes incredibly powerful. As the cloud collapses, as the material gets closer to the center, any initial rotation gets amplified. Remember the figure skater pulling in their arms? The same thing happens with a collapsing gas cloud. As the cloud shrinks, any tiny rotation it had becomes faster and faster. Let me put some numbers on this. Suppose a gas cloud 1 light year across has a barely perceptible rotation, completing 1 turn every billion years. That's an incredibly slow spin, far too slow to notice. But as the cloud collapses to form a star, it might shrink by a factor of 10 million or more. Conservation of angular momentum means the rotation rate increases dramatically. What was 1 rotation per billion years becomes many rotations per day. The imperceptible wobble becomes a dramatic spin. This is why every star, every planet, every moon, every galaxy has some rotation. The collapse that formed them amplified whatever tiny initial asymmetry existed. Conservation of angular momentum turned imperceptible wobbles into the dramatic spins we observe. It's not that rotation was somehow added during formation. It's that the rotation that was always there, hidden in the initial conditions, became concentrated and visible. This connection between deep principles and observable phenomena is what Feynman found most beautiful about physics. The spin of a galaxy isn't just a random feature that happened to develop. It's a direct consequence of the fact that the laws of physics don't have a preferred direction. It's symmetry made visible on the grandest possible scale. Let me give you a preview of how powerful this principle is. Consider why the solar system is flat. About 4.6 billion years ago, a vast cloud of gas began to collapse to form the Sun and planets. That cloud had a tiny amount of rotation. As it collapsed, conservation of angular momentum transformed a barely perceptible spin into rapid rotation. And because the collapsing material couldn't shed its angular momentum, it settled into a flat rotating disk rather than a sphere. This is why all the planets orbit in nearly the same plane, all going the same direction. It's not coincidence. It's angular momentum conservation made visible. We'll explore this process in detail later, but the same physics applies everywhere. Every star system, every galaxy formed through processes shaped by this conservation law. The ubiquity of rotation in the cosmos is a direct manifestation of the universe's rotational symmetry. Now, let me explain angular momentum in more precise terms, because understanding this will help us see why it's so fundamental. In classical mechanics, angular momentum is defined relative to some point, usually called the origin or the axis of rotation. For a single particle, the angular momentum combines the particle's position and its momentum in a specific mathematical way. It captures both how fast something is moving and how far it is from the reference point and in what direction. For a solid object like a spinning top, you add up the angular momentum contributions of all the particles that make up the object. The result is a total angular momentum that points along the axis of rotation. For a top spinning counterclockwise when viewed from above, The angular momentum vector points upward. This vector nature of angular momentum is important. Angular momentum isn't just a number. It's a quantity with a direction, and that direction is conserved along with the magnitude. This is why a gyroscope maintains its orientation. The angular momentum vector resists changing direction, and it takes a torque, a rotational force, to alter it. Torque is to angular momentum what force is to regular momentum. Just as a force changes an object's momentum, a torque changes an object's angular momentum. And just as momentum is conserved in the absence of external forces, angular momentum is conserved in the absence of external torques. In an isolated system with no external influences, the total angular momentum remains constant forever. This is why planets keep orbiting. This is why stars keep spinning. This is why galaxies maintain their rotation over billions of years. There's nothing to stop them. No torque is being applied to change their angular momentum. Consider this thought experiment, which Feynman often used in his teaching. Imagine you're doing an experiment in a laboratory. You set up your equipment, run the experiment, and get certain results. Now imagine rotating the entire laboratory, including yourself, by some angle. You set up the same experiment and run it again. Do you get the same results? Experience tells us yes. The laws of physics don't depend on which direction your laboratory faces. Gravity pulls down regardless of whether you're facing north or east. Electromagnetic forces work the same way, no matter how you orient your equipment. The strong and weak nuclear forces don't care about your laboratory's orientation. This rotational invariance of the laws of physics is the symmetry that gives rise to conservation of angular momentum. It's not a coincidence that angular momentum is conserved. It's a mathematical necessity given the symmetry of physical laws. In his lectures, Feynman would ask students to imagine trying to define absolute direction in space. How would you tell someone far away which direction is north? You might point to a star, but that star is in a particular direction only from your location. You might try to use the Earth's magnetic field, but that's a local phenomenon, not a universal standard. There is no cosmic arrow pointing in a preferred direction. Space itself is rotationally symmetric. And because space is rotationally symmetric, because the laws of physics are the same regardless of direction, angular momentum must be conserved. The universe has no mechanism for angular momentum to simply appear or disappear. It can only be redistributed. This principle operates at every scale. When an ice skater spins up, they're not creating angular momentum. They're converting the arrangement of their mass into faster rotation while keeping the total constant. When a collapsing gas cloud spins faster as it shrinks, it's not creating angular momentum. The total remains what it was. The rotation just becomes more concentrated, more intense, but there's still more to the story. We've talked about classical angular momentum, the kind associated with objects moving in circles or spinning on axes. But there's another kind of angular momentum that's even more fundamental. It's called spin, and it exists at the quantum level. In the quantum world, particles like electrons possess an intrinsic angular momentum called spin. Remarkably, this isn't due to the electron physically rotating like a tiny ball. Spin is something stranger, a fundamental quantum property with no classical equivalent. We'll explore quantum spin in depth later, but for now, the key point is this. Even at the subatomic level, angular momentum exists and is conserved. The same principle that keeps planets orbiting also governs the behavior of the electrons. The same rotational symmetry that Noether identified operates at every scale. And this quantum spin has profound consequences. It determines how atoms bond to form molecules. It explains why matter is stable and why the periodic table has the structure it does. Rotation isn't just something that happens in the universe. It's woven into the very fabric of how matter is organized. All of this, from the quantum spin of electrons to the rotation of galaxies, traces back to the same underlying principle. The universe has rotational symmetry. The laws of physics are the same regardless of direction. This symmetry guarantees the conservation of angular momentum. And this conservation shapes everything from the structure of atoms to the formation of stars and planets to the dynamics of galaxies. This unity is what Feynman called the beauty of physical law. The same mathematics that describes the spin of an electron describes the orbit of a planet. The same conservation law that keeps a gyroscope stable keeps galaxies rotating for billions of years. The same rotational symmetry that prevents you from defining absolute direction in space also determines the chemical properties of elements. This unification is one of the most remarkable features of physics. Phenomena that seem completely unrelated, the behavior of subatomic particles and the motion of celestial bodies, turn out to be governed by the same principles. Understanding those principles lets you understand an enormous range of phenomena with a small number of deep ideas. The universe spins because it has no reason not to. There's no preferred direction that would allow rotation to dissipate. There's no mechanism to remove angular momentum from an isolated system. Once something is rotating, it keeps rotating forever unless something acts on it to transfer that angular momentum elsewhere. And because perfect stillness would require perfect symmetry, which quantum mechanics forbids through the uncertainty principle, there's always some rotation, some angular momentum, somewhere in any real physical system. This is the truth that Feynman helped uncover and explain. Not just that angular momentum is conserved, but why it's conserved. Not just that conservation has consequences, but what those consequences are at every scale, from atoms to galaxies. The spinning of stars and galaxies isn't just a feature of the universe that happened to develop. It's a necessary consequence of the universe's fundamental symmetry. Given the rotational symmetry of physical law, it couldn't be any other way. In the next part of our journey, we'll explore the mathematics behind this connection more deeply. We'll see how Emmy Noether proved her remarkable theorem and understand why the connection between symmetry and conservation is so powerful. And we'll appreciate even more deeply why everything in the universe, from the smallest particle to the largest galaxy, simply must spin. To truly understand why everything in the universe spins, we need to dive deeper into one of the most beautiful ideas in all of physics: the connection between symmetry and conservation laws. This connection was first proven mathematically by Emmy Noether in 1918, but its full significance was appreciated and expanded upon by physicists throughout the 20th century, including Richard Feynman. Let me start by explaining what physicists mean by symmetry, because it's slightly different from the everyday meaning of the word. In everyday language, we might say a face is symmetric if the left and right sides look roughly the same. A snowflake is symmetric because it looks identical when rotated by 60 degrees. A circle is symmetric because it looks the same from any angle. These are examples of symmetry in the colloquial sense, referring to shapes and patterns that have certain regularities. But physics generalizes this concept in a powerful way. In physics, a symmetry is a transformation that leaves something unchanged. If you can perform some operation on a system, and the system looks exactly the same afterward, or behaves exactly the same way, that's a symmetry. The operation might be a rotation, a translation in space, a translation in time, a reflection, or something more abstract that doesn't correspond to any simple physical motion. The key insight, the revolutionary idea that Noether formalized, is that the laws of physics themselves have symmetries. The equations that describe how the universe works remain unchanged under certain transformations. This isn't about particular objects being symmetric. It's about the fundamental rules of nature being symmetric. Consider spatial translation. If you pick up your entire laboratory and move it 100 miles to the east, will your experiments give different results? No. An electron behaves the same way in New York as it does in Tokyo. Gravity works identically in your backyard and on the moon. Chemical reactions proceed the same way in different countries. The laws of physics are the same everywhere in space. This is called translational symmetry, and it's not a symmetry of any particular object. It's a symmetry of the laws of physics themselves. Consider rotation. If you turn your laboratory to face a different direction, will your experiments give different results? Number. Gravity doesn't pull harder when you face north than when you face east. Electromagnetic forces don't change depending on how you orient your equipment. Nuclear reactions don't care which way your particle accelerator points. The laws of physics are the same in all directions. This is rotational symmetry. Consider time translation. If you run an experiment today versus tomorrow, assuming all conditions are the same, will you get different results? No. The laws of physics don't change over time. An experiment performed in ancient Egypt, if conditions were identical, would give the same results as one performed today. This is temporal symmetry, the sameness of physical law across time. These symmetries seem almost trivially obvious when you state them. Of course, the laws of physics are the same everywhere. Of course, they don't depend on what direction you face. Of course, they don't change from day to day. These seem like statements so obvious they barely need saying. But Emmy Noether showed that these obvious symmetries have profound, non-obvious consequences. Noether was born in 1882 in Erlangen, Germany. She faced enormous obstacles as a woman trying to enter mathematics. German universities didn't officially admit women when she began her studies. She had to audit courses and needed special permission to take exams. Even after earning her doctorate, she couldn't hold a regular faculty position for years. The famous mathematician David Hilbert championed her cause, reportedly saying that the university was not a bathhouse and that sex should not matter for academic appointments. Despite these obstacles, Noether made fundamental contributions to abstract algebra and theoretical physics. Her theorem connecting symmetries to conservation laws, published in 1918, is considered one of the most important results in mathematical physics. Einstein called her the most significant creative mathematical genius, since the higher education of women began. Noether's theorem states that every continuous symmetry of a physical system corresponds to a conserved quantity, and conversely, every conserved quantity corresponds to a symmetry. The word continuous is important here. It means symmetries that can be performed in arbitrarily small amounts, like rotating by tiny angles or moving by tiny distances, as opposed to discrete symmetries like reflection. Let's unpack what this means for each of the symmetries we discussed. Translational symmetry, the fact that the laws of physics don't change from place to place, gives rise to conservation of momentum. If you push a ball in empty space and nothing pushes back, it keeps moving forever in a straight line at constant speed. Momentum, the product of mass and velocity, is conserved. This isn't just an observed fact. It's a mathematical necessity given translational symmetry. If space is the same everywhere, momentum must be conserved. Why is this? Here's an intuitive way to understand it. If the laws of physics were different in different places, a particle could speed up or slow down just by moving from one region to another. It could gain or lose momentum based on where it was, but if the laws are the same everywhere, there's no reason for the momentum to change. The particle has no way of knowing it moved because the physics is identical in the new location. So momentum stays constant. Temporal symmetry, the fact that the laws of physics don't change over time, gives rise to conservation of energy. Energy cannot be created from nothing or destroyed into nothing because the rules of the game don't change as time passes. If the laws were different tomorrow than today, you could potentially extract unlimited energy by exploiting the differences. But since the laws are unchanging, energy is conserved. And rotational symmetry, the fact that the laws of physics don't prefer any direction, gives rise to conservation of angular momentum. Rotation persists because the universe is the same in all directions. If there were a preferred direction, angular momentum could drain away toward that direction. But since all directions are equivalent, rotation has nowhere to go. It must be conserved. This is remarkable when you really think about it. The conservation laws that govern the behavior of everything from atoms to galaxies aren't arbitrary rules imposed from outside. They're not commandments handed down without explanation. They're necessary consequences of the universe's structure. They couldn't be otherwise without the laws of physics being different in different places or directions or times. Let me try to explain the connection between rotational symmetry and angular momentum conservation in a way that captures the essence without requiring advanced mathematics. Imagine a particle moving through space. At any moment, it has a position and a velocity. The laws of physics tell us how the velocity changes over time, based on the forces acting on the particle. Newton's laws, or their more sophisticated modern versions, provide the equations of motion. Now consider rotating the entire situation. The particle's position rotates to a new position. Its velocity rotates to a new velocity. The forces, if any, rotate to new directions. If the laws of physics are rotationally symmetric, then this rotated situation evolves according to exactly the same laws as the original situation. The rotated particle will move in a way that's just a rotated version of how the original particle would move. This means that if you take any solution to the equations of motion and rotate it, you get another valid solution. The physics is unchanged by rotation. Any trajectory is just as good as any rotated copy of that trajectory. Noether's theorem tells us that this invariance implies a conserved quantity. The mathematics, which involves calculus and differential equations, works out so that the conserved quantity is precisely angular momentum. If the laws are unchanged by rotation, then a certain combination of position and momentum, specifically the cross product of position and momentum vectors, remains constant over time. This might seem abstract, so let me give a concrete example that makes the connection clear. Consider a planet orbiting a star. The gravitational force between them points directly toward the star. It's what physicists call a central force, meaning it always points toward the center. There's no component of the force pushing the planet sideways, only pulling it inward. Central forces have perfect rotational symmetry about the center. If you rotate the entire system, the planet and star, and the gravitational force between them, the physics is completely unchanged. The force still points toward the center. The equations of motion are identical. There's no preferred direction in the plane of the orbit. Noether's theorem tells us that this rotational symmetry implies conservation of angular momentum about the center. The planet's angular momentum, calculated relative to the star, must remain constant throughout its orbit. And indeed, this conservation has observable consequences. Johannes Kepler discovered his second law of planetary motion empirically in the early 1600s by analyzing years of careful observations of Mars's orbit compiled by the astronomer Tycho Brahe. Kepler's second law states that a line drawn from a planet to the sun sweeps out equal areas in equal times. This equal area law is exactly equivalent to conservation of angular momentum. When the planet is closer to the sun, it moves faster. When it's farther away, it moves slower. The product of distance and velocity, which relates to angular momentum, stays constant. Kepler had no idea why this law was true. He simply noticed the pattern in the data. It took Isaac Newton, working decades later, to show that Kepler's second law was a consequence of the inverse square law of gravity, combined with conservation of angular momentum. Newton understood that central forces conserve angular momentum, and he could derive Kepler's law mathematically. And it took Emmy Noether 2 centuries after Newton to show that conservation of angular momentum is itself a consequence of rotational symmetry. She provided the deepest level of explanation, showing that the conservation law is inevitable given the symmetry of nature. This chain of understanding, from Kepler's empirical law to Newton's dynamics to Noether's theorem, represents one of the greatest achievements of human thought. We've gone from observing that planets move in certain ways to understanding that they must move in those ways given the fundamental symmetries of nature. The planets have no choice. Given rotational symmetry, angular momentum conservation follows as a mathematical necessity, and given angular momentum conservation, Kepler's equal area law follows inevitably. In his lectures, Feynman would stress that physical laws aren't arbitrary. They're constrained by symmetry. If the universe has certain symmetries, then certain quantities must be conserved. There's no freedom in the matter. The conservation laws are as inevitable as the symmetries themselves. This has profound implications for cosmology. When we observe that everything in the universe rotates, we're not seeing a random feature that happened to develop. We're seeing a manifestation of the universe's rotational symmetry. The angular momentum exists because the universe has no preferred direction, which means angular momentum must be conserved, which means any angular momentum present at early times persist forever, which means the tiny initial rotations get amplified and concentrate as structures form. But where did the angular momentum come from in the first place? If angular momentum is strictly conserved, if it can never be created, then the total angular momentum of the universe should be constant from the very beginning. So either the universe started with some angular momentum, or there's something more subtle going on. The answer involves both the initial conditions of the universe and the way angular momentum is distributed within it. First, let's consider the total angular momentum of the entire observable universe. This is actually a subtle question, because angular momentum is always measured relative to some reference point, and there's no obvious center of the universe to use as a reference. The universe has no edge, no center, no preferred location. How do you even define total angular momentum for something like that? Cosmologists have thought carefully about this question, and the evidence suggests that the total angular momentum of the observable universe might be very close to zero. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, show no evidence for overall cosmic rotation. The universe appears to be isotropic, the same in all directions, to very high precision. But this doesn't mean nothing rotates. It means the rotations roughly cancel out when you add them all up. For every galaxy rotating clockwise as seen from some vantage point, there's another galaxy somewhere rotating counterclockwise. For every star system with angular momentum pointing one way, there's another with angular momentum pointing the opposite way. The net angular momentum sums to something close to zero. Think of it like a room full of spinning tops. Each top is spinning vigorously, but half are spinning clockwise and half counterclockwise. The total angular momentum of all the tops together might be nearly zero, even though each individual top has substantial angular momentum. But even if the total is zero, individual regions can have significant angular momentum. How does this happen without violating conservation? How can rotation exist if the total is zero? The answer is that angular momentum can be transferred between systems. It cannot be created or destroyed, but it can be redistributed. Consider two bodies interacting gravitationally. As they pull on each other, they can exchange angular momentum. One might spin up while the other spins down. One might gain orbital angular momentum while the other loses it. The total remains constant, but the distribution changes. Angular momentum flows from one object to another, like water flowing between connected containers. The total amount of water stays constant, but it can slosh from one container to another. There's one more aspect of this story I want to address. It's the question of where the original asymmetries come from that give rise to angular momentum in the first place. We've established that perfect symmetry would mean no rotation, but where do the imperfections come from? The answer traces back to the very beginning of the universe. Quantum mechanics guarantees that perfect uniformity is impossible. In the early universe, this meant tiny fluctuations in both density and velocity. These primordial imperfections, though incredibly small, were enough to seed rotation. When matter later collapsed under gravity, These initial asymmetries were amplified. We'll explore this cosmic origin story in detail when we examine the larger scales, but the key point is that the angular momentum of galaxies can ultimately be traced back to quantum physics, operating in the first moments after the Big Bang. As the universe evolved, gravity amplified these initial fluctuations. Regions that were slightly denser attracted more matter and collapsed to form structures. During a collapse, gravitational interactions redistributed angular momentum. Some regions gained it, others lost it. The cosmic total might be near zero, but individual structures accumulated substantial rotation. There's another important aspect of symmetry worth discussing. It relates to the difference between global and local symmetries. A global symmetry is one where you perform the same transformation everywhere at once. Rotating the entire universe by some angle is a global transformation. Every point in space gets rotated by the same amount simultaneously. The laws of physics are invariant under such global rotations, and this invariance gives rise to global conservation of angular momentum. A local symmetry is something different and in some ways more powerful. It's a symmetry where you can perform different transformations at different points in space. You might rotate by 10 degrees at one location and by 20 degrees at another. Local symmetries are more restrictive because they require the laws of physics to be invariant under this much broader class of transformations. Local symmetries turn out to be at the heart of our modern understanding of fundamental forces. The gauge symmetries underlying electromagnetism and the nuclear forces are local symmetries. When you require the equations of physics to be invariant under certain local transformations, you're forced to introduce force-carrying particles like photons and gluons. The forces of nature emerge as consequences of local symmetry requirements. For angular momentum, the relevant symmetry is global rotational symmetry. We don't require the laws to be invariant under different rotations at different points. The connection to angular momentum conservation comes from global, uniform rotations of the entire system. But in general relativity, Einstein's theory of gravity, things become more subtle. In general relativity, spacetime itself is dynamic. It curves and warps in response to matter and energy. There's no fixed background space against which you can easily define rotation. This makes the definition of angular momentum more challenging in general relativity. In flat spacetime, angular momentum is straightforward to define, but in curved spacetime, especially in regions of strong curvature like near black holes, the concept becomes more nuanced. There are technical difficulties in even defining what total angular momentum means for certain spacetimes. For most practical purposes, including the formation of stars and planets and galaxies, ordinary Newtonian physics with its straightforward conservation of angular momentum works extremely well. The corrections from general relativity are tiny except in extreme situations, but at the extremes, near black holes and in the very early universe, the full machinery of general relativity becomes necessary, and the relationship between symmetry and conservation becomes more sophisticated. Let me return to the broader significance of what we've discovered, because it illuminates why the connection between symmetry and conservation is so intellectually important. As Feynman put it, conservation laws allow you to make predictions without knowing all the details. You don't need to track every atom in a collision to predict that total momentum will be conserved before and after. You don't need to calculate the complete detailed trajectory of every particle in a planet to know its angular momentum will stay constant. Conservation laws let you skip the details and go straight to conclusions. This is immensely powerful. Real systems are complicated. A galaxy contains hundreds of billions of stars, each interacting gravitationally with all the others. Calculating the exact motion of every star is impossible. But conservation of angular momentum tells you that regardless of all those complicated interactions, the total angular momentum of the galaxy isn't going anywhere. You can make predictions about the whole system without solving the impossibly complex dynamics of every component. Conservation laws are powerful precisely because they transcend details. They apply regardless of the specific forces at work, regardless of the complexity of the system, regardless of everything except the fundamental symmetries. If rotational symmetry holds, angular momentum is conserved. Period. No exceptions, no special cases, no need to know anything else about the system. A universe without rotational symmetry would be a universe where angular momentum isn't conserved. Imagine what such a universe would be like. Rotation could appear from nowhere and disappear into nothing. A stationary wheel might spontaneously start spinning. A gyroscope might randomly change its orientation. Planets might stop orbiting without any collision or external force. The stable structures we depend on, from atoms to solar systems, couldn't exist in their familiar forms. The fact that our universe does have rotational symmetry, and therefore does conserve angular momentum, is crucial for stability at every scale. Atoms are stable partly because electron angular momentum is quantized and conserved. Solar systems are stable because planetary angular momentum is conserved. Galaxies maintain their rotation for billions of years because there's no mechanism for that rotation to dissipate. The various conservation laws are also interconnected. Energy, momentum, and angular momentum are all related to symmetries of spacetime. In the mathematical language of modern physics, they're all generators of the Poincare group, the set of transformations that leave the structure of flat spacetime unchanged. Energy is associated with time translation, momentum with space translation, angular momentum with rotation. They form a unified mathematical structure. When you combine spacetime symmetries with quantum mechanics, things become even more interesting. In quantum mechanics, angular momentum is quantized. It comes only in discrete units, multiples of Planck's constant divided by 2 pi. An electron can have spin 1/2 or -1/2 measured along any axis, but nothing in between. An atom's electron orbitals have specific quantized amounts of orbital angular momentum, 0 or 1 or 2 units, never 1.5. This quantization is why atoms have the structure they do. The different electron orbitals correspond to different values of angular momentum. The periodic table of elements, which organizes all of chemistry, reflects the quantized angular momentum states of electrons in atoms. The chemical properties of carbon and oxygen and iron arise from which angular momentum states their electrons occupy. And this quantization of angular momentum is itself connected to rotational symmetry, but in a subtle quantum mechanical way. In quantum mechanics, states of definite angular momentum are states that transform in specific ways under rotation. The mathematics of rotation in quantum mechanics, called representation theory, determines which values of angular momentum are possible. Feynman explored these connections throughout his career. His path integral formulation of quantum mechanics provides a particularly elegant way to understand how symmetries give rise to conservation laws. In the path integral approach, to calculate the probability of a quantum particle going from point A to point B, you sum over all possible paths the particle could take. Each path contributes to the total amplitude with a weight determined by the action. Symmetries manifest as invariances of the action. If rotating a path doesn't change its action, then rotational symmetry holds. And when symmetries hold, conservation laws emerge automatically from the mathematics. The path integral makes this connection particularly transparent. The spinning of the universe from atoms to galaxies is a testament to the power of these ideas. Everything spins because the universe is rotationally symmetric. It's as simple as that, and as profound. So when we ask why everything spins, the full answer involves multiple connected levels of explanation. At the deepest level, rotation exists and persists because the laws of physics are rotationally symmetric, which guarantees conservation of angular momentum through Noether's theorem. At the level of initial conditions, tiny quantum fluctuations in the early universe provided the primordial asymmetries that gave different regions their initial, minuscule amounts of angular momentum. And at the level of structure formation, gravitational collapse amplified these initial asymmetries, concentrating the angular momentum into smaller and smaller volumes, making it visible in the form of spinning stars, orbiting planets, and rotating galaxies. This coherent story, connecting symmetry to conservation to cosmic structure, exemplifies what Feynman meant when he spoke of the beauty of physical law. The spin of a top, the orbit of the moon, the rotation of the Milky Way, all are manifestations of the same underlying reality. A universe governed by symmetric laws where angular momentum, once it exists, can never disappear. Now that we understand the deep principles behind rotation, the connection between symmetry and conservation that Feynman helped illuminate, let's explore how angular momentum actually manifests across the incredible range of scales in the universe. From the strange quantum spin of subatomic particles to the majestic rotation of forming star systems, the same conservation law applies everywhere. But the phenomena look remarkably different depending on what scale you're examining. Let's start at the smallest scale we know of, with quantum spin. Every electron in the universe has exactly the same amount of intrinsic angular momentum. Not approximately the same, exactly the same. To the limits of our ability to measure, every electron ever observed has had the same spin. This universality is one of the deepest mysteries in physics. Why should all electrons be identical? Why should they all have the same spin? We don't have complete answers. But the fact itself is beyond question. This spin, as physicists call it, is not due to the electron actually spinning like a tiny top or a miniature planet. In fact, if you try to model an electron as a small spinning sphere, you quickly run into serious problems that show this picture cannot be correct. Here's the difficulty. The electron has a very small mass, about 9.1 times 10 to the negative 31 kilograms. That's about 2,000 times lighter than a proton. The electron also has a very small size. Actually, as far as we can tell, The electron has no size at all. Our best experiments can only establish that if the electron has any spatial extent, it must be smaller than about 10 to the negative 18 meters. That's a billion times smaller than an atom. Yet despite this tiny or possibly zero size, the electron has a definite, measurable angular momentum. We can measure it precisely in experiments. It always comes out to be 1/2 times the fundamental quantum unit of angular momentum, which is Planck's constant divided by 2 pi. Now, if you try to calculate how fast the surface of a tiny spherical electron would have to be moving to produce this observed angular momentum, you get a velocity larger than the speed of light. That's impossible according to special relativity. Einstein showed that nothing can travel faster than light. This means the electron cannot be a spinning sphere in any literal sense. So electron spin is not ordinary rotation. It's not the electron physically whirling around like a top. It's something stranger. A quantum mechanical property that has the same mathematical structure as angular momentum, obeys the same conservation laws, but doesn't correspond to any motion we can visualize. Feynman grappled with this strangeness throughout his work on quantum electrodynamics. Early in his career, he tried various ways of understanding spin in more intuitive terms. Eventually, he came to accept that spin is simply a fundamental property of particles, not reducible to any classical motion or any simpler concept. It's as basic as mass or electric charge. You can't explain why electrons have the mass they have. Similarly, you can't explain why they have the spin they have. It's just a fundamental fact about how the universe is constructed. Electron spin takes only 2 values when measured along any axis. Physicists usually call these spin up and spin down. In the standard units, these correspond to +1/2 and -1/2. There's no spin 1/4 or spin 3/8, just up or down, nothing in between. This discreteness, this quantization, is part of what makes quantum mechanics so different from classical physics. In the classical world, things can vary continuously. A top can spin at any speed, but in the quantum world, certain quantities only come in discrete chunks. Spin is one of these quantized quantities. The behavior of quantum spin is genuinely strange, with no classical analog. If you measure an electron's spin along the vertical axis and find its spin up, what happens if you then measure along a horizontal axis? You don't get a definite answer. Instead, you get spin left or spin right with certain probabilities, each 50% if the axes are perpendicular. The act of measuring along the horizontal axis disturbs the state, and subsequent measurements along the vertical axis will again give random results. This isn't like a spinning top where you could in principle know the complete state of its rotation. Quantum spin doesn't work that way. The electron doesn't secretly have definite spin values along all axes simultaneously. Before measurement, the spin along a given axis doesn't have a definite value. The measurement creates the value, in some sense. But here's what's remarkable and what connects to our main story. Even though quantum spin is strange and counterintuitive, it still satisfies conservation of angular momentum. When particles interact, when they collide or decay or are created in pairs, the total angular momentum before the interaction must equal the total angular momentum after. This includes both orbital angular momentum, the kind associated with particles moving through space in curved paths, and spin, the intrinsic quantum kind. This conservation law puts powerful constraints on particle physics. Many reactions that you might imagine could happen simply don't occur because they would violate angular momentum conservation. If a particle with spin 1 decays into 2 particles, those 2 particles must have spins that add up correctly. If a particle with spin 0 decays, the products must have spins that cancel out to 0. These rules are inviolable. The mathematical equations that describe quantum field theory, our deepest understanding of how particles behave, automatically incorporate angular momentum conservation. They're built on the same rotational symmetry that gives rise to Noether's theorem at the classical level. The quantum version is more sophisticated mathematically, but the principle is the same. Feynman's famous diagrams, which represent particle interactions graphically and which he developed in the late 1940s, implicitly include angular momentum conservation at every vertex. Every point in a Feynman diagram where particles meet and interact conserves angular momentum. This isn't something you have to add separately. It's built into the mathematical rules for constructing and calculating the diagrams. When Feynman developed these techniques, he was encoding deep symmetry principles in a practical computational tool. The spin of particles has consequences that extend far beyond abstract physics. It determines the structure of matter. Electrons in atoms occupy orbitals, regions of space where they're likely to be found when you look for them. Each orbital can hold at most 2 electrons, one with spin up and one with spin down. This is a consequence of the Pauli exclusion principle, discovered by Wolfgang Pauli in 1925. The Pauli exclusion principle states that no 2 electrons in an atom can have exactly the same set of quantum numbers. Since each orbital corresponds to a specific set of spatial quantum numbers, and spin can only be up or down, only 2 electrons can fit in each orbital. Any additional electrons must go into different orbitals with higher energy. This principle is itself related to spin in a deep way. Particles with half-integer spin, like electrons with their spin 1/2, are called fermions. All fermions obey the Pauli exclusion principle. They cannot occupy the same quantum state. Particles with integer spin, like photons with their spin 1, are called bosons. Bosons don't obey the exclusion principle. Multiple bosons can and do pile into the same quantum state. This distinction between fermions and bosons has enormous consequences. It determines the structure of atoms, which determines chemistry, which determines what kinds of molecules can exist, which determines the possibilities for life. The Pauli exclusion principle is why atoms have the sizes they do, and why matter takes up space. Without it, all the electrons in an atom would collapse into the lowest energy orbital, and atoms would be much smaller and very different. The distinction also determines the stability of stars. White dwarfs, the remnants of ordinary stars after they exhaust their nuclear fuel, are supported against gravity by electron degeneracy pressure. This pressure arises because the Pauli exclusion principle prevents electrons from all occupying the same state. As a white dwarf is compressed, electrons are forced into higher energy states, and they resist this compression. This quantum effect supports a white dwarf against its own gravity. Neutron stars, even denser objects formed when massive stars explode, are supported by neutron degeneracy pressure. Neutrons are also fermions with spin 1/2, so they also obey the exclusion principle. The cores of neutron stars are the densest stable matter known, supported entirely by quantum effects related to spin. All of this traces back to the rotational properties of particles. How a particle transforms mathematically when you rotate the coordinate system determines its spin. Its spin determines whether it's a fermion or boson, and whether it's a fermion or boson determines how it interacts with other identical particles. Rotation is woven into the very fabric of particle physics and the structure of matter. Let's move up in scale to atoms and molecules, where quantum effects still dominate, but we start to see structures more familiar from everyday experience. In an atom, electrons exist around the nucleus. I use the word orbit carefully, because they don't orbit like planets around a sun, following definite paths. Instead, electrons occupy quantum mechanical probability distributions, clouds that describe where the electron might be found if you looked. These clouds have characteristic shapes determined by the angular momentum of the electron state. The simplest orbitals, called s orbitals, have zero orbital angular momentum. An electron in an s orbital isn't circulating around the nucleus at all in the classical sense. Its probability cloud is spherically symmetric, the same in all directions, centered on the nucleus. The electron might be found anywhere in this spherical cloud. The next type of orbital, called p orbitals, have 1 unit of orbital angular momentum. Their probability clouds are shaped like dumbbells, elongated along particular axes. There are 3 p orbitals oriented along the x, y, and z axes. An electron in a p orbital has definite angular momentum, and is more likely to be found in the lobes of the dumbbell than elsewhere. Higher orbitals have more complex shapes. D orbitals have 2 units of angular momentum, and come in 5 different orientations with intricate shapes. F orbitals have 3 units, and even more complex geometries. The shapes get progressively more complicated as angular momentum increases. This quantization of orbital angular momentum explains why electron orbitals have these specific shapes, and no others. The allowed values of angular momentum are determined by the mathematics of rotation in quantum mechanics. Only certain wave functions are consistent with the requirement that the electron's state be single-valued after a complete rotation. This requirement picks out exactly the orbitals we observe. The periodic table of elements, which organizes all of chemistry, reflects this structure. The rows of the periodic table correspond to filling successive electron shells. The blocks of the table correspond to filling A's, P, D, and F orbitals. The chemical properties of elements arise from which orbitals their outermost electrons occupy. Carbon behaves differently from oxygen because their electrons fill different orbitals. When atoms bond to form molecules, the angular momentum of the electrons rearranges. Electrons from different atoms share orbitals, creating chemical bonds. The shapes of molecules depend on how these orbitals overlap and combine, but angular momentum is conserved throughout all these rearrangements. The total angular momentum of a molecule, including contributions from electron orbital motion, electron spin, and the rotation of the nuclei themselves, remains constant over time. Molecules can rotate as rigid or semi-rigid bodies, tumbling through space. And this molecular rotation is also quantized. A molecule spinning faster has more angular momentum, but only certain discrete amounts are allowed. The energy of molecular rotation is quantized as well, and this affects how molecules absorb and emit light. When a molecule absorbs a photon, it can be promoted to a higher rotational state. When it emits a photon, it can drop to a lower one. The wavelengths of light that molecules absorb depend on the spacing between their rotational energy levels, which depends on their moments of inertia, which depends on their shapes and masses. Molecular spectroscopy, the study of what wavelengths of light molecules absorb and emit, depends crucially on these quantized rotations. Astronomers use molecular spectroscopy to identify what molecules exist in space. By analyzing the light from distant gas clouds, they can determine which molecules are present. Carbon monoxide, water, ammonia, and hundreds of other molecules have been identified in interstellar space through their characteristic spectral signatures, all of which arise from their quantized rotational and vibrational states. Moving up to macroscopic objects, we leave the quantum realm and enter the classical world where angular momentum can take any value, not just discrete quantized amounts, but the same conservation law applies, and many of the same principles govern behavior. Consider a simple spinning top. You set it spinning with a flick of your wrist, and it maintains its rotation until friction gradually slows it down. In an idealized world with no friction and no air resistance, the top would spin forever. The angular momentum you put in at the start stays there because there's no mechanism to remove it. Conservation of angular momentum keeps it spinning. The top also exhibits a phenomenon called precession, a slow wobble of its spin axis. If you watch a top carefully, you'll see that the axis doesn't just point straight up. It traces out a cone, the tip slowly circling while the top continues to spin rapidly around its own axis. This precession is itself a consequence of angular momentum conservation. Gravity exerts a torque on the top, trying to tip it over. You might expect the top to simply fall, but instead, the torque changes the direction of the angular momentum vector without changing its magnitude. The result is that the axis precesses, tracing out a cone rather than simply falling. This is exactly what happens with Earth's rotational axis. Earth isn't a perfect sphere. It bulges slightly at the equator because of its rotation. The gravitational pull of the Sun and Moon on this equatorial bulge creates torques that cause Earth's axis to precess. Earth's axis traces out a complete cone once every 26,000 years approximately. This means the North Celestial Pole, the point in the sky that Earth's axis points toward, slowly drifts against the background of stars. Right now, Polaris is close to the North Celestial Pole, which is why we call it the North Star. But this wasn't always the case, and it won't remain so. 4,000 years ago, when the ancient Egyptians were building pyramids, the pole was near the star Thuban in the constellation Draco. 12,000 years from now, the bright star Vega will be near the North Celestial Pole. Notice that Earth's angular momentum is nearly conserved through all of this. The magnitude stays almost constant. What changes is the direction, and even that changes very slowly over thousands of years. The torques from the Sun and Moon are tiny compared to Earth's enormous angular momentum. The fundamental conservation law holds to excellent approximation. Now let's consider the formation of our solar system, because this is where angular momentum conservation produces some of its most dramatic and visible effects. About 4.6 billion years ago, in a relatively unremarkable region of the Milky Way, a cloud of gas and dust began to collapse under its own gravity. This cloud, sometimes called the solar nebula, was vast, perhaps a light year across. That's almost 10 trillion kilometers. It was made mostly of hydrogen and helium, the simplest elements, with traces of heavier elements like carbon, oxygen, silicon, and iron. These heavier elements had been created by earlier generations of stars that had exploded and scattered their processed material into space. Like all real physical systems, this primordial cloud wasn't perfectly symmetric. It had slight variations in density from place to place. It had slight motions in different parts, inherited from whatever disturbances had triggered its collapse. Maybe a nearby supernova sent a shockwave through the region. Maybe a passing star gravitationally perturbed it. Whatever the cause, the cloud wasn't perfectly uniform, and it wasn't perfectly stationary. These tiny asymmetries meant the cloud had a small amount of net angular momentum. As the cloud collapsed under its own gravity, conservation of angular momentum transformed it dramatically. The cloud had to shrink by an enormous factor. It started perhaps a light year across. The sun that eventually formed is less than 1 light second across, about 1.4 million kilometers in diameter. That's a reduction in size by a factor of more than 30 million. The same principle that speeds up a spinning skater who pulls in their arms applies here, but on a vastly larger scale. As the cloud shrank, any rotation it had sped up proportionally. The angular momentum stayed constant, but it became concentrated into a smaller and smaller volume. A slow, barely perceptible rotation became a much faster spin. But angular momentum conservation didn't just speed up the rotation. It also shaped the collapse itself. Material at the outskirts of the cloud, falling inward under gravity, was also moving sideways due to the rotation. This material couldn't fall straight toward the center because that would require it to shed its angular momentum, and there was nowhere for that angular momentum to go. It had to be conserved. So instead of falling straight in, the material spiraled inward. Matter coming from different directions met and collided, but matter coming from the same direction in the rotation just accumulated. The result was that the cloud flattened into a disk. Material could fall toward the central plane of the disk easily, because that motion doesn't change angular momentum much. But material couldn't easily move inward toward the center, because that would require losing angular momentum. This is why the solar system is flat. The planets all orbit in nearly the same plane, called the ecliptic plane. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all have orbital tilts within a few degrees of this plane. They all orbit in the same direction, counterclockwise when viewed from above Earth's North Pole. This isn't coincidence. It's a direct consequence of angular momentum conservation during the formation process. The original cloud's angular momentum determined the orientation and direction of the disk, and the planets formed within that disk. The sun formed at the center, where the density became high enough for nuclear fusion to ignite. About 99.86% of all the mass in the solar system ended up in the sun. But here's something interesting. The Sun contains only about 2% of the solar system's total angular momentum. The planets, especially Jupiter, contain the vast majority. This distribution tells us something important about how the solar system formed. The Sun didn't simply absorb all the material that fell toward it. As material spiraled inward through the disk, much of its angular momentum was transferred outward. The material fell in, but the angular momentum stayed out in the disk and eventually in the planets. Exactly how this angular momentum transport happened is still an active area of research. Magnetic fields threading the disk probably played a crucial role, creating forces that allowed angular momentum to flow outward while mass flowed inward. Gravitational interactions between different parts of the disk also contributed. The details are complex and not fully understood, but the end result is clear. Angular momentum was redistributed, concentrating mass in the center while spreading rotation throughout the disk. Within that disk, solid particles began to stick together. First, microscopic dust grains accumulated into millimeter-sized particles. Then those gathered into pebbles, then rocks, then kilometer-sized objects called planetesimals. Each collision, each merger, conserved angular momentum while redistributing it among the growing bodies. Eventually, runaway growth produced planetary embryos, objects the size of small planets. These embryos swept up material in their orbital zones, growing larger and clearing gaps in the disk. The giant planets, Jupiter and Saturn, grew large enough to capture hydrogen and helium gas from the disk, becoming the gas giants we see today. The inner planets, including Earth, formed mostly from rocky and metallic materials. The entire process took about 100 million years, perhaps less. At the end, the solar system had something like its current configuration. 8 planets, numerous moons, millions of asteroids, and billions of comets, all carrying angular momentum inherited from the original cloud. But the spins of the individual planets are not simple. They don't all point in the same direction, perpendicular to the disk. Various collisions and gravitational interactions during the chaotic final stages of planet formation altered the spin rates and axial tilts. Venus rotates backward. Its spin axis is tipped more than 170 degrees from vertical, which means it rotates in the opposite direction from its orbit. A Venusian day is longer than a Venusian year. Why is Venus spinning backward? We're not entirely sure. One possibility is that a massive collision early in its history knocked it over. Another is that tidal interactions between Venus's thick atmosphere and the solid planet gradually flipped its rotation over billions of years. Both mechanisms might have contributed. Uranus is tipped on its side, with its axis of rotation lying almost in the plane of its orbit. During parts of its 84-year orbit around the Sun, one pole points almost directly at the Sun, while the other faces away into darkness. The most likely explanation is a collision with an Earth-sized object early in Uranus's history that knocked it sideways. Angular momentum was conserved in that collision, but it was redistributed dramatically. Earth's 23.4 degree axial tilt, which gives us our seasons, is probably the result of the giant impact that formed the Moon. About 4.5 billion years ago, a Mars-sized object called Theia struck the early Earth in a glancing collision. The impact was so energetic that it partially melted both bodies and ejected a vast amount of debris into orbit. This debris coalesced to form the Moon. The collision also tilted Earth's axis and transferred angular momentum between the Earth and Moon. This brings up an important principle. Angular momentum can be transferred between objects through collisions and gravitational interactions. The total is always conserved, but the distribution among different bodies can change dramatically. The Earth-Moon system is a beautiful ongoing example of angular momentum transfer. The Moon is slowly receding from Earth, currently at a rate of about 3.8 centimeters per year. We know this precisely because Apollo astronauts left retroreflector arrays on the lunar surface, and we can bounce laser beams off them to measure the Earth-Moon distance with millimeter precision. Why is the Moon moving away? The answer involves tidal interactions. The Moon's gravity raises tides on Earth, bulges in the oceans, and to a lesser extent in the solid Earth itself. But Earth is rotating faster than the Moon orbits, completing one rotation every 24 hours, while the Moon takes 27.3 days to orbit. Earth's rotation drags the tidal bulges slightly ahead of the line connecting Earth and Moon. The gravitational pull between these offset bulges and the Moon transfers angular momentum. Angular momentum flows from Earth's rotation to the Moon's orbit. Earth's rotation slows down while the Moon's orbit expands. The total angular momentum of the system stays constant, but it gets redistributed. As a result, Earth's day is getting longer. Not by much, only about 1.4 milliseconds per century. But over billions of years, this adds up. When the Moon first formed, Earth's day may have been only 5 or 6 hours long. The tidal interaction has been slowing Earth's rotation ever since, and it will continue into the far future. This same process occurs throughout the solar system. Tidal interactions between planets and their moons constantly transfer angular momentum. Mars's moon Phobos is spiraling inward rather than outward, because Phobos orbits faster than Mars rotates. Tidal forces are stealing angular momentum from Phobos's orbit and transferring it to Mars's rotation. In about 50 million years, Phobos will either crash into Mars or break apart from tidal stresses to form a ring. Jupiter's large moons exhibit complex tidal interactions. Io, Europa, and Ganymede are locked in an orbital resonance, their periods in the ratio 1 to 2 to 4. Every time Ganymede completes one orbit, Europa completes 2 and Io completes 4. This resonance is maintained by gravitational interactions that pump energy and angular momentum between the moons. The tidal heating this produces makes Io the most volcanically active body in the solar system. It may also maintain the liquid water ocean that likely exists beneath the Europa's icy surface. Let's consider binary stars, because they illustrate angular momentum conservation in a particularly clean astronomical context. About half of all stars in our galaxy are in binary or multiple star systems. 2 stars orbit their common center of mass, each tracing out an elliptical path around the point between them where their gravitational influences balance. The angular momentum of such a system is the sum of the orbital angular momenta of both stars plus any spin angular momentum from their individual rotations. As binary stars evolve, their properties can change dramatically while angular momentum is conserved. Consider a binary where one star is more massive than the other. The more massive star will evolve faster. exhausting its nuclear fuel first. When it does, it will expand into a red giant, its outer layers swelling to perhaps 100 times their original size. If the binary is close enough, these expanding outer layers can reach the companion star. Mass begins to flow from the giant to its partner. But mass isn't the only thing transferred. Angular momentum comes with it. The accreted material carries orbital angular momentum that gets added to the receiving star. This mass transfer can dramatically alter the orbits. If mass flows from the more massive star to the less massive one, the orbit typically widens. The system adjusts to conserve angular momentum while accommodating the new mass distribution. If one star eventually explodes as a supernova, blowing away much of its mass asymmetrically, the angular momentum carried away by the ejected material can kick the remaining binary into an entirely different orbit, or disrupt it entirely, sending both stars flying off in different directions. Some binary stars are so close that they interact strongly throughout their lives. These include cataclysmic variables, where a white dwarf accumulates material from a companion. The material doesn't fall straight onto the white dwarf. Because it carries angular momentum, it spirals in, forming an accretion disk. The physics of this disk is governed entirely by angular momentum conservation. Material can only move inward if it transfers its angular momentum outward to other material in the disk. The disk glows brightly from the friction as material spirals in, and occasionally undergoes dramatic outbursts. Neutron stars provide perhaps the most extreme examples of angular momentum conservation in action. A neutron star forms when a massive star, perhaps 10 to 25 times the mass of our Sun, exhausts its nuclear fuel and its core collapses. The core, which might be about the size of the Sun, compresses down to a ball of neutrons only about 20 kilometers across. This is an enormous compression, a factor of about 30,000 in radius, and conservation of angular momentum means that any rotation gets amplified by a corresponding factor. A star that was rotating once every few days might have a core rotation period of several seconds. When that core compresses by a factor of 30,000, the rotation period decreases by a factor of 30,000 squared, because angular momentum depends on both radius and velocity. The result is a neutron star that might rotate several times per second. Some neutron stars rotate much faster than this because they've been spun up by accretion. Material falling from a companion star carries angular momentum that spins up the neutron star. The fastest known pulsar rotates 716 times per second. Its surface is moving at a significant fraction of the speed of light. These millisecond pulsars are the fastest spinning objects we know of in the universe, and they exist because of angular momentum conservation. Pulsars, which are neutron stars that emit beams of radiation from their magnetic poles, serve as extremely precise cosmic clocks. Because angular momentum is conserved, their rotation rates are very stable. We can measure these rotation rates to incredible precision, tracking tiny changes over years or decades. The gradual slowdown of pulsars as they radiate energy and angular momentum tells us about the physics of matter at nuclear densities, conditions we could never reproduce in any laboratory. At every scale we've examined, from the spin of individual electrons to the rotation of a neutron stars, angular momentum conservation governs what happens. The rules are always the same. Total angular momentum is constant. It can flow between objects but cannot be created or destroyed. Fast rotation emerges when angular momentum concentrates into smaller volumes. The direction of the angular momentum vector persists unless torques act to change it. This universality is what makes physics so powerful. The same conservation law that explains why a figure skater speeds up when pulling in their arms also explains why the solar system is flat, why neutron stars spin so fast, and why the moon is slowly receding from Earth. Understanding the principle gives you insight into phenomena across vastly different scales. Feynman deeply appreciated this universality. He often said that nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. The thread of angular momentum conservation runs through quantum mechanics, atomic physics, planetary science, and stellar astrophysics. By grasping this one thread, we understand an enormous range of apparently unrelated phenomena. The universe isn't a collection of disconnected facts to be memorized separately. It's a coherent structure governed by a small number of deep principles. Rotational symmetry and the conservation of angular momentum that follows from it comprise one of the most important of these principles. From the spin of an electron, to the orbit of a planet, to the rotation of a forming star, the same fundamental truth applies. And this brings us to the largest scales of all, to galaxies and beyond, where angular momentum shapes the structure of the universe itself. We've explored how angular momentum governs the quantum world and shapes the formation of stars and planets. We've seen the same conservation law at work from electrons to neutron stars. Now let's venture to the largest scales of all, where rotation manifests in some of the most spectacular and profound ways imaginable. Galaxies spinning through the void. Black holes dragging space-time itself into rotation. And the ultimate question of whether the entire universe might be spinning. Galaxies are not static collections of stars floating motionless in the darkness of space. They rotate. The Milky Way, our home galaxy, completes one full rotation approximately every 225 million years. That's sometimes called a cosmic year or a galactic year. The Sun has orbited the galactic center roughly 20 times since Earth formed 4.6 billion years ago. Think about what this means. All the stars we see in the night sky, every constellation that ancient humans named, every point of light that has inspired poets and navigators and dreamers throughout history, all of them are being carried along in this vast cosmic spin. Orion, the Big Dipper, Sirius. Every single one is moving with us around the galactic center at roughly 230 kilometers per second. That's over 500,000 miles per hour. You don't feel it because everything around you is moving together, just as you don't feel Earth's rotation or its orbit around the sun, but the motion is real and relentless. How does a galaxy come to rotate? The same basic process that spins up a star system, just on a vastly larger scale. In the early universe, perhaps a few 100 million years after the Big Bang, matter was distributed in enormous clouds of gas and dark matter. These proto-galactic clouds were immense, spanning millions of light years. And like all real physical systems, they weren't perfectly symmetric. They had slight variations in density. They had slight motions inherited from the primordial fluctuations seeded during cosmic inflation. These tiny asymmetries meant each cloud had some small amount of net angular momentum. As these clouds began to collapse under their own gravity, conservation of angular momentum took over. The cloud shrank from millions of light years across to structures roughly 100,000 light years across in the case of large spiral galaxies like the Milky Way. That's a reduction of perhaps a factor of 10 or more. And as they shrank, any rotation sped up proportionally. Angular momentum spread thinly across an enormous volume, became concentrated in a much smaller region. But there's a crucial difference between the formation of a galaxy and the formation of a star. Stars shrink down to compact objects. Our sun is about 1.4 million kilometers across. Galaxies don't do this. They settle into extended rotating structures, disks that maintain their size rather than continuing to collapse. Why doesn't a galaxy just keep shrinking? The answer involves a key distinction between different types of matter. Gas can radiate energy but cannot radiate angular momentum. When gas clouds collapse, different streams of gas collide with each other. These collisions convert the kinetic energy of bulk motion into heat, random thermal motion of molecules. This heat can then be radiated away as light, photons that carry energy out into space. The gas loses energy and sinks deeper into the gravitational well, but angular momentum is different. Photons can carry away energy, but a cloud of gas cannot simply radiate away its rotation. Angular momentum is conserved. The gas can shed energy but not spin. The result is that the gas settles into the configuration with the lowest energy that's consistent with its angular momentum. And that configuration is a flat rotating disk. The gas can't collapse any further toward the center because that would require shedding angular momentum. It can't expand outward because gravity pulls it in. The equilibrium is a disk where the outward centrifugal effect from rotation exactly balances the inward gravitational pull at every radius. This is why spiral galaxies have the beautiful flat disk shapes we observe. The disk is not arbitrary. It's the inevitable outcome of gravitational collapse while conserving angular momentum. Dark matter, the mysterious invisible substance that makes up most of a galaxy's mass, behaves differently. Dark matter interacts gravitationally, but not electromagnetically. It doesn't collide with itself in the same way gas does. It can't radiate energy as light because it doesn't interact with photons. As a result, dark matter halos remain extended and roughly spherical. They provide the gravitational scaffolding, the skeleton within which the visible galaxy forms. The visible components of galaxies, the stars and gas clouds and dust that we can observe with telescopes, are embedded within these dark matter halos. The rotation of the visible disk is supported by the combined gravity of both the visible matter and the invisible dark matter. In fact, observations of galactic rotation were among the first evidence for dark matter's existence. The outer parts of galaxies rotate faster than they should based on the visible matter alone. The additional gravity of dark matter explains the observed rotation curves. This picture explains why different types of galaxies have different shapes. Spiral galaxies like the Milky Way and Andromeda have flat disks because they formed from gas that could radiate energy and settle into a disk while conserving angular momentum. Their beautiful spiral arms, the iconic pinwheel shapes we see in astronomical photographs, arise from density waves that propagate through these rotating disks. Elliptical galaxies, which are more spherical or football-shaped, have different formation histories. Many ellipticals form through mergers of spiral galaxies. When two spiral galaxies collide and merge, the orderly rotation of their disks is scrambled into more random motions. The stars end up orbiting the galactic center on all different tilts and orientations, producing a roughly spherical shape. Angular momentum is still conserved during mergers, but it gets redistributed among many stars moving in many directions. So the net organized rotation is much less than in a spiral. The spiral arms themselves are fascinating structures related to galactic rotation. A common misconception is that spiral arms are fixed collections of stars, like the spokes of a wheel. They're not. If they were, differential rotation would wind them up and destroy them within a few galactic rotations. The inner parts of a galaxy orbit faster than the outer parts, so a fixed arm would quickly wrap around the galaxy and disappear. Instead, spiral arms are density waves, regions of slightly higher density that propagate through the disk. Stars and gas clouds enter the spiral pattern, slow down as they pass through the compressed region, and then exit on the other side. The pattern persists even as individual stars move through it, like a traffic jam that stays in place even as individual cars pass through. The density wave theory explains how spiral patterns can persist for billions of years despite differential rotation. The mathematics is complex, involving gravitational instabilities and resonances in the disk, but the key point is that the existence and behavior of spiral arms depend entirely on angular momentum. The rotation of the disk, the different orbital speeds at different radii, the gravitational interactions that sustain the spiral pattern, all are consequences of angular momentum conservation operating on galactic scales. Now let's consider black holes, because they represent angular momentum conservation taken to its most extreme and mind-bending limit. A black hole forms when a massive star exhausts its nuclear fuel and its core collapses. For stars above a certain mass threshold, roughly 3 times the mass of our Sun for the final collapsed core, no known force can halt the collapse. Not electron degeneracy pressure, which supports white dwarfs. Not neutron degeneracy pressure, which supports neutron stars. Nothing. The matter falls inward without limit, crushing itself to infinite density at a point called the singularity. Surrounding the singularity is the event horizon, the boundary of no return. Anything that crosses the event horizon, matter, light, information, can never escape. The event horizon is not a physical surface. There's nothing there you could touch or see if you fell through. It's simply the boundary beyond which the escape velocity exceeds the speed of light, making escape impossible according to the laws of physics as we understand them. But collapsing stars have angular momentum, and that angular momentum must be conserved. The core of a massive star is typically rotating, perhaps once every few seconds. When that core collapses by a factor of 100,000 or more to form a black hole, the rotation speeds up enormously. The result is a rotating black hole. And rotating black holes are very different from non-rotating ones. The physics of rotating black holes was worked out by Roy Kerr, a New Zealand mathematician who found the solution to Einstein's equations for a spinning black hole in 1963. This Kerr solution, as it's called, describes the space-time geometry around a rotating black hole, and it has remarkable properties. First, the singularity is different. Instead of a point, a rotating black hole has a ring-shaped singularity. The intense spin prevents complete collapse to a single point, spreading the singular region into a ring in the equatorial plane. Second, the event horizon is different. For a non-rotating black hole, the event horizon is a perfect sphere. For a rotating black hole, it bulges at the equator, flattened by the spin like a ball of pizza dough that's been tossed. The faster the rotation, the more oblate the horizon becomes. Third, and most remarkably, a rotating black hole drags space-time itself around with it. This effect is called frame dragging or the lens-thirring effect. Near a rotating black hole, space itself is pulled into rotation. Anything in that region, matter, light, anything at all, is forced to move in the direction of the black hole's rotation, even if it starts out moving the opposite way. This isn't just theoretical speculation. Frame dragging has been observed. Gravity Probe B, a satellite launched by NASA in 2004, carried extremely precise gyroscopes designed to measure frame dragging caused by Earth's rotation. Earth is not a black hole, and its rotation is modest, so the effect is tiny. Gravity Probe B measured a precession of the gyroscopes of about 39 milliseconds per year. That's an incredibly small angle, about 1/10,000,000th of a degree per year. But it matched the prediction from general relativity, confirming that rotating masses really do drag space-time. Near a supermassive black hole, frame dragging is far more dramatic. The supermassive black hole at the center of our Milky Way, called Sagittarius, a star, has a mass of about 4 million times the mass of our Sun. All that mass is concentrated in a region smaller than the orbit of Mercury. It's almost certainly rotating, and possibly rotating quite rapidly, near the maximum possible rate for a black hole of its mass. The space-time near Sagittarius A star is twisted and warped by this immense angular momentum. Stars orbiting close to the black hole trace paths that are affected by frame dragging. The Event Horizon Telescope, which produced the first image of a black hole's shadow in 2019, is beginning to probe these effects directly. Frame dragging has important astrophysical consequences. Material falling toward a black hole doesn't fall straight in. Because it carries angular momentum, it spirals inward, forming a swirling accretion disk around the black hole. The rotation of the black hole affects how this disk behaves. For a rapidly rotating black hole, the innermost stable orbit, the closest distance at which matter can orbit without spiraling in, is much closer to the event horizon than for a non-rotating black hole. Material can orbit closer before finally plunging in. This has consequences for how much energy can be extracted from infalling matter. The closer matter can orbit, the more gravitational energy it releases as heat and radiation before crossing the event horizon. Rapidly rotating black holes are more efficient engines for converting matter into energy. The powerful jets that some black holes produce, narrow beams of matter and energy that can extend for thousands or even millions of light years, are thought to be powered in part by the black hole's rotation. The Blanford-Snarjek mechanism, proposed in 1977, describes how magnetic fields threading an accretion disk can extract energy directly from a rotating black hole's spin. This is remarkable. The black hole's angular momentum, the rotation that was conserved through the collapse that formed it, becomes a source of energy. The spin gradually decreases as energy is extracted, but the total angular momentum of the system, including the energy carried away by the jets, is conserved. Feynman spent part of his career working on the relationship between gravity and quantum mechanics, though a complete theory of quantum gravity remains one of the great unsolved problems in physics. One of the deep questions in this field concerns what happens to angular momentum when something falls into a black hole. In classical general relativity, when matter crosses the event horizon, its angular momentum is added to the black hole's spin. The black hole's total angular momentum increases, and this can be measured from outside by observing how the black hole affects its surroundings. Angular momentum is conserved, but quantum mechanics complicates this picture. Stephen Hawking showed in 1974 that black holes aren't truly black. They emit radiation, now called Hawking radiation, due to quantum effects near the event horizon. This radiation causes the black hole to slowly evaporate, losing mass over enormous timescales. The puzzle is that Hawking radiation appeared to be thermal, carrying no information about what fell into the black hole. If a spinning object falls in, does the Hawking radiation somehow encode that angular momentum? Or is the information lost? This is related to the famous black hole information paradox, one of the deepest problems in theoretical physics. Most physicists believe that information, including angular momentum, must somehow be preserved, even if we don't yet understand the mechanism. The symmetry principles that guarantee conservation laws seem too fundamental to be violated even by the extreme physics of black holes. But exactly how information escapes a black hole, encoded in subtle correlations in the Hawking radiation, remains an active area of research. Let's zoom out even further and ask a remarkable question. Does the entire universe rotate? If the universe had an overall rotation, a cosmic spin, it would have observable consequences. The cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space, would show characteristic patterns. Certain asymmetries in how this radiation is distributed across the sky would reveal cosmic rotation. Astronomers have searched carefully for such signatures. So far, no evidence of cosmic rotation has been found. The universe appears to be non-rotating to very high precision. The best current limits suggest that if the universe rotates at all, it completes less than one rotation in the entire age of the universe, 13.8 billion years. This might seem surprising at first. Everything within the universe rotates, from atoms to galaxies. Why doesn't the universe as a whole spin? But when you think about it more carefully, it makes sense. Angular momentum is conserved. If the total angular momentum of the universe was zero at the beginning, it must remain zero forever. Individual parts of the universe can rotate, can have substantial angular momentum, but these rotations must approximately cancel out overall. For every galaxy spinning clockwise as seen from some vantage point, there's another galaxy somewhere spinning counterclockwise. For every pulsar spinning one way, there's another spinning the opposite way. The vast cosmic ledger balances to zero, or very close to it. This cancellation isn't perfectly exact. There might be some slight net rotation. Some researchers have claimed to detect subtle asymmetries in the distribution of galaxy spins, a slight preference for one-handedness over another. These claims are controversial and not widely accepted. The current scientific consensus is that any cosmic rotation is too small to detect with current observations. There's also the intriguing question of angular momentum in the large-scale structure of the universe. Galaxies aren't randomly scattered through space. They're organized into filaments and walls and clusters, a vast cosmic web of matter. Some studies have found that galaxies within filaments tend to align their spin axes with the direction of the filament. This alignment might be a relic of how the filaments formed, with tidal talks between different parts of the cosmic web generating correlated angular momentum during structure formation. This field of cosmological angular momentum is still developing. Large surveys are mapping the spins of millions of galaxies, looking for patterns that might reveal how angular momentum is distributed and correlated across the universe. The data is becoming rich enough to test detailed predictions from cosmological simulations. What about the very early universe? In the first moments after the Big Bang, did angular momentum play a role? During cosmic inflation, a period of exponential expansion that occurred perhaps 10 to the negative 36 seconds after the Big Bang, quantum fluctuations in the inflaton field were stretched to cosmic scales. These microscopic quantum fluctuations became the seeds of all large-scale structure. The tiny density variations they created eventually grew through gravitational instability into galaxies and clusters and the cosmic web. These primordial fluctuations weren't just density fluctuations, they were also velocity fluctuations. Different regions of the universe were moving in slightly different directions, and these velocity fluctuations included rotational components, tiny vorticities and swirls. When matter later collapsed to form galaxies, these primordial velocity fluctuations provided the initial angular momentum. The rotation of galaxies today can be traced back through billions of years of cosmic evolution to quantum fluctuations during inflation. The same quantum mechanics that Feynman spent his career developing, the theory that describes electron spin and particle physics, also set the initial conditions for the rotation of galaxies. This connection between the quantum and cosmic scales is real and profound. It's not a metaphor or an analogy. The quantum fluctuations are literally the source of cosmic structure. The uncertainty principle operating at scales smaller than an atom during inflation produced variations that now span millions of light years. Let me now bring our entire journey together. We started with a simple observation. Everything in the universe spins. The earth beneath your feet rotates. The moon orbits us. We orbit the sun. The sun orbits the galactic center. Galaxies spin. Even fundamental particles have intrinsic spin. From the smallest scales we can probe to the largest structures we can observe. Rotation is ubiquitous. We asked why, and found the answer in one of the deepest principles of physics. The laws of nature are symmetric under rotation. Space doesn't have a preferred direction. You can orient yourself however you like, and the laws of physics work identically. This symmetry, through the mathematics of Noether's theorem, implies that angular momentum must be conserved. Conservation of angular momentum means that rotation, once it exists, persists forever in the absence of external torques. Angular momentum can be transferred from one object to another. It can be concentrated into smaller volumes, making rotation faster. It can be spread out over larger regions, making rotation slower, but it cannot be created from nothing or destroyed into nothing. The total is always preserved. The rotation we see in the universe today is not random or accidental. It's the rotation that was present from the earliest times, conserved and redistributed through billions of years of cosmic evolution. The initial rotation came from quantum fluctuations during inflation, tiny primordial asymmetries that quantum mechanics made unavoidable. When structures formed through gravitational collapse, these fluctuations were amplified. Conservation of angular momentum turned imperceptible quantum wobbles into the dramatic spins of stars and galaxies. At every scale we examined, the same principle applied. Quantum spin, governed by the mathematics of rotation in quantum mechanics, electron orbitals, shaped by quantized angular momentum, molecular rotation, determining how molecules absorb and emit light, spinning tops and gyroscopes, maintaining their orientation through angular momentum conservation, planet formation, explaining why the solar system is flat and why all the planets orbit in the same direction, binary stars, exchanging angular momentum as they evolve, neutron stars, spinning hundreds of times per second because of angular momentum concentrated during collapse, galactic rotation, with disk shapes arising from gas that could radiate energy but not angular momentum, black holes, dragging spacetime itself into rotation through frame dragging, and the universe as a whole, apparently non-rotating because the cosmic total is zero. The details differ enormously across these scales. Quantum spin is strange and has no classical analog. Galactic dynamics involves billions of stars and vast amounts of dark matter. Black hole physics requires general relativity and pushes toward the unknown territory of quantum gravity. But the underlying principle is always the same. Angular momentum is conserved because the universe is rotationally symmetric. Richard Feynman appreciated this unity more than almost anyone. He understood that physics is not a collection of separate phenomena to be memorized independently. It's a coherent structure governed by a small number of deep principles. Symmetry and conservation are among the deepest. The same thread of angular momentum conservation runs through quantum mechanics, planetary dynamics, stellar evolution, galactic astronomy, and cosmology. By grasping this one thread, we understand an astonishing range of phenomena. Feynman often spoke of the beauty of physical law. He didn't mean merely aesthetic beauty, though physics can certainly be aesthetically pleasing. He meant the beauty of ideas that are simple, yet powerful, that unify diverse phenomena under common principles, that allow you to understand why things happen the way they do rather than just cataloging what happens. Angular momentum conservation is one of the most beautiful ideas in this sense. It's simple to state, angular momentum is conserved. But from this simple principle flows an enormous wealth of consequences. The shapes of galaxies, the flatness of the solar system, the stability of gyroscopes, the extreme spin of pulsars, the efficiency of black hole jets, all from one principle which itself follows from one symmetry. And this raises profound questions we still can't fully answer. Why does the universe have rotational symmetry? Why are the laws of physics the same in all directions? These symmetries aren't logically necessary. We can imagine universes where directions matter, where the laws of physics depend on your orientation. We can write down mathematical equations that violate rotational symmetry. Why doesn't our universe work that way? Some physicists appeal to the anthropic principle. Perhaps universes without certain symmetries don't allow complex structures to form. Without angular momentum conservation, planetary systems might be unstable. Stars might not form properly. The complex chemistry needed for life might not occur. So perhaps we observe rotational symmetry because we couldn't exist without it. We're here to ask the question only because the universe has the properties that allow us to exist. Others seek deeper explanations. Perhaps rotational symmetry emerges from some more basic principle we haven't discovered yet. String theory, loop quantum gravity, and other approaches to fundamental physics make predictions about space-time symmetries. The ultimate theory of physics, if we ever find it, might explain why the symmetries we observe are what they are. For now, we can marvel at what we know. The universe spins because its laws are rotationally symmetric. This symmetry guarantees conservation of angular momentum through Noether's theorem. This conservation shapes the formation of structures at every scale, and the rotation we observe today connects through an unbroken chain of cause and effect back to quantum fluctuations in the first instance after the Big Bang. You are part of this story in a literal sense. The atoms in your body were forged in the cores of rotating stars. The heavier elements, carbon, oxygen, iron, were created by nuclear fusion and then scattered into space when those stars exploded. The debris formed new rotating clouds that collapsed into new rotating stars with rotating planets. On one such planet, rotating on its axis while orbiting its star, life emerged and evolved. And here you are, made of atoms from rotating stars, standing on a rotating world, orbiting a rotating sun in a rotating galaxy. Rotation isn't something that happens out there in the distant cosmos, separate from your everyday experience. It's woven into your existence at every level. The spin of electrons determines the chemistry of the atoms you're made of. The rotation of Earth gives you day and night. The orbital angular momentum of Earth gives you years. You're not just observing the spinning universe, you're part of it. The next time you watch a spinning top, or see the stars wheel overhead during a long night, or contemplate a photograph of a spiral galaxy, remember what you've learned. You're seeing one of the deepest truths of physics made visible. The universe spins because it must. Its fundamental rotational symmetry demands nothing less. This is the truth that Feynman helped illuminate through his life's work. The rotation of the cosmos is not random or arbitrary. It's a necessary consequence of the structure of physical law. In a universe where all directions are equivalent, angular momentum is eternal. And so everything that can spin does spin, and continues spinning across the vast reaches of space and the immense stretches of cosmic time. The spinning of stars and galaxies is not just a feature of the universe we happen to observe. It's a signature of the universe's deepest nature. When you understand why everything spins, you understand something fundamental about reality itself. You've grasped one of the threads that holds the cosmos together, and that understanding connects you to every thinker who has pondered these questions throughout history. From ancient observers who tracked the wheeling stars, to Kepler analyzing the orbit of Mars, to Newton deriving the laws of motion to Noether, proving her profound theorem to Feynman, illuminating quantum mechanics and symmetry. You're part of a tradition of wonder and inquiry that spans centuries and continues today. The universe is vast and ancient and strange beyond imagination, but it's also comprehensible. We can understand why things happen as they do. We can trace the rotation of galaxies back through billions of years to quantum fluctuations. We can connect the spin of an electron to the deepest symmetries of physical law. We can ask why everything spins and actually find an answer. This ability to understand, to find patterns and principles amid the complexity, is perhaps the most remarkable thing about the human mind. Feynman said that science is like an adventure. The further you go, the more you see, and what you see is more wonderful than you could have imagined at the start. The story of cosmic rotation is exactly such an adventure. It begins with a simple question: why does everything spin? And leads through the deepest ideas in physics to a profound appreciation of the universe's elegant structure. Thank you for joining me on this journey through the spinning cosmos. If you found it enlightening, a like or subscribe would mean a lot. It helps bring these explorations of the universe to more curious minds. And remember, as you go about your life on this spinning planet in this spinning galaxy, you're participating in one of the most ancient and universal phenomena in existence. You are part of the cosmic dance, the same angular momentum that emerged from quantum fluctuations near the beginning of time, that was conserved through billions of years of cosmic evolution, that shaped the stars and planets and galaxies. That same angular momentum carries you through another day on Earth. Sleep well under the stars. They're spinning, just like everything else. And now, you know why. Good night.